Welcome. What I'm talking about today is a historical view of real-time feeder event monitoring that we've been performing with a large investor-owned utility for the last several years, and the interesting information above and beyond data, but the information that we've learned from it, and then what we were able to do to come back and install solutions so that not only are we monitoring, but we're also detecting and then notifying. Okay, so my name is John McGowan, Global ANSI Product Manager for Distribution Automation. Our office is in Coral Springs, Florida, which is a suburb of Miami. And then I'm also located in Bethlehem, Pennsylvania, which is an adjunct group, an office with some research and development people for the productization of our products, and our product portfolio that I'm responsible for, distribution, protection, and control relays. And that involves all technologies, electromechanical that we still make, solid state, and then of course microprocessor-based technology. And then I'm basically with the development folks as they develop my products for delivery to the market. The history of this project, it's a wonderful project we've had, as I mentioned, with an investor-owned utility, basically serving to marry their needs with our innovative technologies. And then where we may not have the technologies to meet their needs and pains, then we have been developing them. And that's what this shows, that history of that. The equipment that we used to collect data and then therefore perform offline analysis and then develop the algorithms. We had various installations of products, so I'll talk about those different installations which are interesting. The fact that when we did come back and implement algorithms that actually can detect and then notify, we talk about those solutions that we have and that are working today. Some interesting case studies that you'll find that I think you'll find unique to this type of pilot. And what I mean by that is you will see the names of the cases. In many cases, they may be pretty typical, a load-in rush, a switching transient. But keep in mind what's happening here is all this activity, primarily, most of it, is actually happening in many cases beyond a fuse. And so your substation equipment data typically does not have the ability, because of their coordination and what they're trying to coordinate with the downstream protection devices. They usually are not fast enough and do not have the capability to actually detect these very short-lived activities beyond a lateral fuse, for example. And so we're going to talk about, that will be interesting. So all those case studies really, in many cases, apply to that. And naturally, there are some that apply to conditions that are monitored and recorded and collected right from the substation. That happened right outside the substation. Reporting. What can we do? What's the kind of value here? Because when you think of information and data and the criticality of when you talk about serving up information through DMP, traditional SCADA connection from the substation to the dispatch center, it's always in a case of a binary. I had a 51P fault, I had a phase time over current fault, an instantaneous fault. Very crude. It's important, but it's still just data, and it's not telling a story. And someone has to study all that information coming back and then create their own story. And of course, many cases, an engineer gets involved and writes a report. This is what happens. So one of the things that we learned with our being able to do all this information and collecting all the data and then learning the information that that is telling us is formulate a report so that we can actually just tell them exactly what's happened. And that will help make an intelligent decision, because as I always say, you have to have intelligent data, intelligent information in order to make an intelligent decision. And then I'll also talk about a project that we have going on right now with basically the U.S. government, Department of Energy, had a program in which they were offering money for research in feeder health and performance management activities. And because of all the work that we have done already with this large utility that you'll see, that actually put us in a very, very lead spot and got selected. We're only one of 5 entities, a consortium that got selected for the funding out of over several hundred, because the history that we had working with the utility, the wonderful history, helped a lot. And then we'll have, and what part of that is going to be the criticality of something, the idea of what can we do in the future with respect to location of the faults. Okay, so this started in 2006, very precisely in September of 2006, where a large utility in the Denver metro area, which of course is just a part of it, it's Xcel Energy, they had some pains, they had some issues. They had a whole infrastructure of very aged, old, 30-plus-year-old underground cable faults. And they know that they believe that these were possibly showing signs of incipient failures, or that is, they were having problems and probably showing that information, but there's nothing that can monitor it. And then, of course, when it finally gets bad enough, it's a permanent fault. And then that's when they have an outage, and the customer has to call, and then they have to go out and find it, and then repair the cable section, the segment of the cable. And that's obviously a lengthy process. It also is reactive because they really don't know until the first customer calls. So one of the things that we started with when we took our research folks there is to say, with the business folks, which is me, who can give them a physical product to test and implement, is can you detect these from the substation? Is there any way, with the data that's in the substation, can you learn if these cable faults are showing early signs of failure? Okay, so we took that challenge. So, as I mentioned, this lasted several years, and because of what we kept learning, we actually expanded in a very positive way. So we started again in 2006, and we basically had about, this just shows the number of substations, the number of feeders that we monitored, and then how many we monitored inside the sub. So you can see that in the first year we were monitoring in the sub, and then already in phase 2, we added some equipment outside the sub, and I'll talk about what that equipment is. Because even though we see the value of having all this information available from inside the sub, where they have the intelligent communications already set up through the SCADA, maybe you might be able to get some more information by having an intelligent device properly located somewhere, let's say in the midsection of the feeder. So we want to just at least learn if that's possible. Then phase 3, you can see what was happening there. We obviously expanded the number of substations. We expanded the number of feeders, the number of monitoring points inside the substation, and the number of monitoring points outside the substation. And then in 2008, we also started, because of that first agreement, we put in an actual real-time detection device for incipient cable faults, underground cable faults. And that's been running ever since, and we've been expanding on that. So 2010, 2011, we've been basically doing all kinds of reporting, analyzing, offline and online. And now, as I mentioned, in 2011, we were awarded the DOE project. So in 2012 is when we're going to have our installation for the first phase of the Department of Energy project with our consortium, and you can see how much we're expanding there. So what are the things that we learned in all these 3 phases? Well, a couple of things we learned was not only were we seeing cable faults, permanent cable faults, and incipient cable faults, and I'll talk about that, but we're seeing a lot of other information, okay, with the typical connections available inside a substation on a feeder, at the head of the feeder. We were able to learn a whole list of different types of feeder events. Now, I'm not saying faults. Notice I raised it up a level, and it's a more general term of events. And so you can see the list there. You'll have this presentation, so you can go through it later. But there's a whole bunch of different types of events that we felt it would be valuable to know, again, information, where there are unique signatures associated with each of these types of feeder events that happen all the time. And knowing that could be very informative for example, a dispatcher. If they dispatch someone to go and put in a cat bank, okay, then you'd have a device that could actually then see the characteristic of a cat bank switch occurring and sort of get confirmation of when that happened. If that cat bank is basically a non-intelligent cat bank, it's simply out there and then you just had to put it on, or maybe opened it. It could be a fixed installation of a cat bank. They just have it connected to the feeder at the right point of that line, and that maybe the dispatcher told them to go out and open it. So they would be able to at least see a signature, almost a verification, if you will, that it happened and when it happened. Besides, of course, the person calling, but at least it's interesting to know that they'll have that information. Some of the other things that we did was, again, non-faults, code load pickup, capacitor bank, and then the faults. We have like a short duration, long duration, which could be useful later on for the fault location and other information for what type of fuse, for example, may have blown. But we're also, because what we're doing is we're identifying the clearing device. We're going to say whether the breaker operated. That's an easy one because the substation breaker is right there. So we can kind of know that one with an A and B contact. But you may have a recloser halfway down the line. You might have fuses, lateral tap fuses. And that when we see these types of faults, we actually attempt to identify the clearing device. And where we know it's a fuse, we actually give an estimated fuse size. And I'll talk more about that later. And so what we're doing then is saying, okay, well, how is this valuable for Xcel Energy? How is it valuable for the utility? Okay, great. Once again, I got all this data, I got all this information, but what can I do with it? Well, again, it's all about having the information. If you can have this information, and particularly before your first customer call, especially when there's an outage or even some terrible dip in the bus voltage, then that can put you in a position to better react to customers, be proactive in how you're working with customers. And then also we had what we did, we used the time to actually select different feeder topologies. So we had, even though they wanted to know about underground cables, we also put in some overhead feeders that had primarily overhead sections. We put in some, we had some feeders we chose that had a mix of underground and overhead. And then some cases we had like an entire bank. So in this case, 4 feeders, and see what kind of information that we can get from having all 4 feeders monitored on one bank. So this is some of the results. What we had was we had more than 3,700 events captured, analyzed, and then confirmed by OMS. Now, there are a lot of them that were not confirmed by OMS, and I'll talk about that, but you'll see it's proof positive that it happened, okay? The pictures don't lie, so you'll see that soon. But so this is a tremendous amount of events. Now, this is not including what I'll talk about is the outside substation equipment, data collection equipment we installed, and also inside the sub that related to a power quality device. The power quality device, that was recording tens of thousands. And so here's a nice spread of these 3,700 events, the breakdown. So you can see how many of the different zones. Okay, now what do zones mean? One of the things I should have had in here was about zones. What we did was we determined that, let's talk about where we all know about zones of protection. So we kind of applied that to this project and said, let's talk about a zone being a primary zone. So if my device is monitoring feeder 1, 2, 3, 4, and I see something on that feeder, that's going to be called my primary zone. It's relative to the device you're referring to, the monitoring device you're referring to. If I have another monitoring device to left and right on the feeders that are next to it but sharing the same bus, but my 1, 2, 3, 4 monitoring device sees something but it's not its feeder, it will then treat it as an adjacent zone. And it's because it's on the same bus, and you'll see how it can determine that. There's also then finally an upstream. We've had many, many transmission events, as you can imagine. They have a whole ring bus set up of different 115 kV, 230 kV feeding these substations, and when there's activity, snowstorms, and all kinds of activity and operations, we actually see that reflected on the secondary side of the power transformer in the substation. So then we have an upstream. So this tells you the different types of zones that we had. Primarily they are primary zone, and then adjacent, and then upstream. Okay. Then we had the different event types. Okay, cable fault, and then the load inrush and the switching transient, and then also for the primary zone. Then for the device we happen to be monitoring, in some cases we only had one device monitoring, so it was sort of like, okay, we hope something happens on that feeder because then we'll have a bunch of primary, but if everything's happening on the other 2 feeders, we didn't do a good job of choosing. We can only put in so much, and now we're getting a lot of adjacents. The good news is that you see we had a lot more primaries than anything else, but in the adjacents we were still able to say the different types of events from this type of list. Okay, so it's sort of an adjacent zone, but I'm still going to say it was a breaker failure. I'm still going to say it was a reclose into the fault. I'm going to say it's a switching transient or a cable fault. But it's not my feeder, it's the feeder next to me. That's what this means, the different events for an adjacent zone. Okay, now another thing we did is set up as we were building this, the customer liked what they were seeing, and they said, well, there's so much more information that we can get. So we then developed algorithms and collected them into a feature called Distribution Feeder Event Analysis, okay, DFEVA. So what this is doing, a comprehensive algorithm that runs on our station computer, COM600. It works with the data that's provided by the station monitoring device. In this case, it's our Relion family distribution feeder protection relay, REF615. which would be right here, the IED that's at the head of the feeder. And then it'd be communicating to the station computer, and then we would actually retrieve all the data from the devices that are there. And if we're going to focus on this guy, okay, then you would see that this is the primary zone with respect to IED1, and therefore anything that happens there would be adjacent to this one, okay? And then there's the upstream zone. It's very generic. It's from the bus all the way up into the transmission, but still very valuable, and it's that you can differentiate. And so then what we're doing when we're getting this information is then we're logging it, and then we are sending essentially a near real-time, okay, we're going through the cloud, but we're sending a near real-time message of the report to the dispatchers. All right, so we can, and I'll talk a little more about that later. So that's like a typical setup and one of our things that we did in the history of this project that just really got installed last year. In phase one, it really were just starting, so it was new. So this is really, these were mouse traps. These are protective relays, feeder protection relays with the station computer. And we were just setting up the settings to kind of capture something. But when you do that, you wouldn't actually be able to then use them for standard protection. Okay, so we're just kind of making it work as a monitoring device. And then it would get sent to the computer, and then the research guys would just dial in once a week and just get the information and do an offline analysis and start building algorithms, okay? But that was how we first started. But you can see the typical setup here. So we got the underground, it could be a recloser, a regulator, and then we have our lateral fuse. And then they're all our pad mounts serving customers. And that's the criticality, is a lot of the faults happen here in the underground, and the fuse blows. And because of that, with the proper coordination and the setting levels, conventional protection relays cannot detect that. It's too fast. Okay, they cannot detect that. Now, what we did when we were excited and captured cable faults, both permanent and incipient, is the algorithm that was built by research folks, I then, working with them as the business unit, then took that algorithm and integrated it into a protection and control relay. Now, what I did was, what protection and control relay would you put that in? If you're monitoring a feeder for feeder events, what kind of protection and control relay would you put it in? Feeder protection relay, right. So now, because it's uniquely different and has its own algorithm running, you don't have to use conventional overcurrent functions, which in many cases will not be able to detect these short-lived instances. And you get the value add. It's the optimal cost-effective solution because it's going to protect your main feeder. It will have all the voltage and current protection for its standard feeder protection and control scheme. And you get the additional benefit of event cable fault detection. And then with the station computer, you also then get the further comprehensive event analysis. This is just an example of the PQ device. When we installed them in a substation, we monitored all the 4 feeders on one bank, so that was the full bank story. So it's just a PQ device, and then it's connected to a router, to a Airlink cell modem, and then through the cloud. Now, we were not in Xcel Energy's network at all. Okay, for safety reasons, I'll talk about what that meant. In some cases, that was a limiting factor for the near real-time notification because we're going to the cloud. But you'll see that we still had very, very good response time. Naturally, as it would be eventually, let's say, accepted by utility, it would be integrated into their protected LAN and WAN, and then that would have the high speeds without the problem of the net. It would stay local. Then we had some external. Remember I said we did some external installations. So it was those same power quality devices right here that we mounted on the terminal pole in this case, and we used Lindsay sensors, and then we had actually a rack of three-phase VTs and made the connections, secondary connections to the input of the power quality device. And then we had a remote connection back to the research folks, and they can retrieve data from it. So this was located, let's say, you could say halfway down the main line. So it was the overhead section and then went underground. Okay. Another interesting one then where we did have the feeders that were all underground, we actually put them in the switch cabinets. All right, so we found room. This is where the utility was fantastic in working with us. They connected the same type of equipment inside the switch cabinet, and they were able to remotely communicate to these devices and get the data, and then do the offline analysis. In this case, Rogowski coils, and then you had the different areas to place the box for protection and the actual sensors. This is the example where we took our cable fault detection algorithm, and we put it into our feeder protection and control relay. So that's what we did there as part of this project, which allowed the customer to get this feature. What's interesting also, of course, if they may have their own standard for feeder protection and control, you can still just use this for monitoring. Okay, so if they want to just have a separate device, that's possible as well. This is a deployment, an installation that we just did March of last year. So when we were awarded the DOE project, and then there was a lot of negotiating going on, we actually still wanted to finish up in sort of the phase 3, the end of the phase 3, the start of DOE. We wanted to implement a real-time detection notification scheme for cable fault events. So we're at a particular substation. We're on 2 different banks. It's a normally open tie. So we have the one Ref 615 with cable fault detection on one feeder, and then we have it on another feeder. And then they are communicating to our station computer COM600 that is running all the DEFIVA algorithms. So these have the dedicated cable fault detection algorithms, and then these have all the other feeder event algorithms to analyze what happened real time. That's the difference. This is a real-time monitoring and analysis. Earlier, we did an offline analysis. We were just building the algorithm, so they just brought it back into the lab. They had the ComTray files, and they developed algorithms and then played them back. So that was the offline. But here, this is taken to the next step, that it's actually now installed and running real time for, is it a load-in rush, a load-in rush, a recloser operation, a fuse fault. Now, we did have just a little feedback. What we had was most of the 191 disturbances that we detected were early. What that meant was the email with the information about that cable fault right here, you can see how short-lived that is. High current, very short-lived. Then that got to the dispatcher before the first customer call. Okay, so they actually had knowledge, information about a cable fault in their system that caused an outage before the first customer called. Some of them were late. Again, I think that really was the cloud. We looked into that. There were some things we did clean up as a first installation. And we missed a few, but that was really, again, first installation. The computer had a problem, and we just had to work it out. And we did work it out. It was just a setup issue. So one of the things that happened then in May, and in fact, it was interesting because I did a similar presentation last year. And we're doing it for a couple years because you can see the phases that we've had, but I'm trying to show everyone how we're growing and building from it. So I think I may have been able to last year talk, well, no, I wasn't, I apologize. This happened after the April APW last year. I'm trying to remember now. But what happened was we got a detection. We all got an email on May 7th, and it was an incipient fault. Why was it incipient? Self-clearing. OMS had no record. No one called. But yet, look at that. That's clearly something. You can't deny that. You know, this is, I mean, that's very clear what that is. And then 20 days later, it failed permanently. I'll show you a much more interesting one. In one case, we actually gave them the notification 4 hours before the first customer called. That was actually serving a park, and I think no one was in the park late at night or something like that, so we got away with that. But it was just pretty interesting that there was over 250 minutes before the first customer call. But they had the information of the feeder, the substation, the date, the time, the phase, because they had this picture in the email. They had this PDF picture of the waveform, so they knew the phase and they knew the magnitude. And by somewhat knowing the magnitude, that could actually help them get an idea. Okay, so let's start talking about some case studies. All right, so here's an incipient cable splice fault, incipient cable fault. September 11, 2007 at 2:42 p.m., 422 amps, okay, right here, RMS. No outages or customer phone calls. And then it permanently failed June 14th, 2008. And in between September 11, 2007 and June 14th, anyone want to guess how many other incipient fault cases we got? How many we saw? 139. 139 detected, you can see, short-lived, high-magnitude faults that cleared themselves because there was not a single OMS record, not a single phone call. And then it finally failed at over 2,600 amps. Now, what do you think it was? What do you think in the end they found it to be? It was a bad cable splice. The biggest activity is June to September, and yet this was September to June. So it was really interesting. Now, because we were kind of new and we were setting this up, and the folks working the distribution system didn't know us, they could have done something like close the normally open switch and at least created a backfeed when this failed so that they wouldn't have gotten taken out all the customers. But, we weren't at that stage where we were confident enough and say, hey, close that normally open switch because that's going to eventually fail. But it was just very interesting. This is the kind of stuff that could be done with the reliability and the confidence buildup from the dispatchers when you're physically looking at that. Now let's talk about here was the May one. So May was 9 p.m., and then the email was received at 9:04 p.m., 2 minutes, and no customer calls. And you can see it's about over 1,300 amps, one phase B. Then May 27th, it happened again at 3:57 a.m. Actually, the first customer call didn't happen until 8:21 a.m. because this fed a park. So I guess that's when they did their walk in the park. But, we had that email to them 9 minutes later. Now, that was even bad. We had to correct something. We usually are 2 minutes, within 2 minutes on the timestamp of the email. But we're going through a general cloud. We're going through our email system. We're going through the XLNG is going through their email system. So, but others were almost the same minute. I was just trying to show what we can do on permanent faults. The value here is with that information and the deployment that we had, we could tell them with the short duration, because of that finer resolution of how long the fault was, that a fuse interrupted it and what size. And in many cases they confirmed, and we have a report we go through every 2 weeks and we see like we're spot on or we missed one. But we'll give an estimate of, hey, we think that's a 65 amp fuse. We think that could be valuable information if they know ahead of time what size fuse blew. A second one happened on March 15, 2011 at 3:04 a.m. We reported it at 3:14 p.m. The customer called at 3:13. So we're saying someone was staying up late and couldn't sleep that night. They actually called before we can get the email. But we were slow there again. But it's pretty funny that they called really early. But obviously that was serving a house, and someone noticed the lights went out. But there's another real-time detection by our Ref 615 serving the information up to the COM600 station computer, and then it's performing the analysis and not only just saying the cable fault with the date and time, the substation, and the feeder name, but also saying that it was interrupted by fuse and the size fuse. We did get some switching operations or transients, so that's just valuable to know. If they are asking someone to go out there and perform a switching operation, this can almost be a confirmation that they performed that switching operation. Or how about they get that and they didn't send anyone out? Okay, so that could be informative, by knowing about this, because again, these waveforms don't lie. Okay, it's not a binary point from SCADA; it's actually the picture. How about an evolving fault? This was an interesting one. There was actually no OMS data. There was no phone call on this, so I'm going to say it was an incipient. But what was interesting was it was an A and then became a B. And possibly because of that, it leaped. That it wasn't long enough for anything, either the fuse to blow, or the recloser, or the substation breaker. But we detected it. Another one, code load pickup. Now, what happened here also we noticed was, if you look at this, what would you say, not only was it picking up some load, but what would you say also happened here? If you look at the magnitude, the RMS magnitude on phase C, what would you say it was also? Okay, because there was a phase A fault. When we caught this, there may have been a phase A fault, and the substation breaker opened and closed, because the reason why would you say it's a substation breaker? We're at the head of the feeder. How would you conclude it's a substation breaker versus a device downstream of the substation? What clue in the waveform, the first waveform, would tell you? But what do you see as a big delta? If you look at that picture just from the 10,000 foot level, what's the biggest difference? Is there any kind of load? You think there's any load there? It's zero. So that's a reasonable estimate that the breaker is actually open at the substation head, and then it closed. And when it closed, it picked up non-faulted phases, the load from the non-faulted phases, and then happened to reclose back into a fault, so it must have been a permanent fault. Here's a substation reclose, and here's the case where you do see the inrush, and then it does settle back down to low currents. So there's some very interesting information there. Moderate effect on the bus voltage, so you can see how it's affecting the bus in the substation based on that. And again, it was on a close because there was zero current before this event. Now, this is an adjacent zone. Remember I said, so we're at the same feeder, but now it saw some current and voltage activity. And it sent that data to the substation computer, COM600, that evaluated what kind of feeder event it was. So when it came out and it said it was an adjacent zone fault, permanent cable fault. So this is the kind of limited information we have, but yet we consider say it's an adjacent fault. We're seeing it, so we must be in the same bus. The feeder's on the same bus. And then with that dip in voltage short-lived, that tells you that fault was on that phase. This is a transmission disturbance. We got a report. We got a whole bunch of reports when it was a winter storm, and they had a 230 to 115 kV transformer bank trip and lockout. And all the feeder incoming, all the substation incomings connected to that ring bus of the 115, where we had recording monitoring devices all recorded. And so this is the kind of activity that you saw. Okay? Now, look at that, because now you can say, well, this is, I don't see a big current, but do you see anything a little different? In a way, there's a lot more activity because it's closer to the bus here, but this is far away. So notice how the bus was not as affected. Okay, so that's like one of the characteristics you can use to say it's an upstream zone fault. So now, when we have this kind of an operation, so we're back to that picture again, the primary zone, the adjacent zone. I've got my Ref 615 at the head with my station computer. I have a fault in the lateral fuse. I can actually give a message that says a cable fault event on phase B has just been detected on the primary feeder, 1234, in this case 1765, at this date, at this time, that was cleared by a 40 amp fuse. And then we even go as far as give a reliability. How confident are we about this report conclusion? And in this case, high, because of all the data that we have. You look at that, you're not surprised we would have a high probability. We really believe that that's the case. We do have the notifications. This is just an example. So this is my email where I get the waveform capture as an attachment. It's a PDF file. And you can see that's where I get the date and time that I use as a quote-unquote that we're notified. And then compare it against the actual fault time in the relay that captured the event. And then you can do all kinds of historical reading, so recording in that station computer. So you can just simply, in a given year, just go out to it and then just see on a web server page all the activity on all the feeders where you're monitoring and get a good history. And that can help the O&M, operation and maintenance, determine what are the best cables to replace for the next budget year. They may have their own list, and what do you think they're primarily using? Age, exactly right. But with this information, guess what? They may learn there was a bad splice on a new cable, and they're going to push that up in the priority list. So this is the kind of value-added decisions, the intelligent decisions that they can make with this information. This is effectively what we're telling them. This is a interpretation, but basically when they get the email, they're getting the type of event. Even in the subject heading of the email, they're finding out whether it's the adjacent zone or the primary zone right away or upstream. They then will know the phase. They will know the magnitude. They'll know the feeder. They'll know the substation, the feeder, the phase, and then they'll have the picture to actually see what the magnitude is. They'll have all that information. So effectively, this is the message being given by having all that information. So in this project, there's a 3-year project that's starting this year. Basically, we won the money to do research on a feeder health and performance management solution. And so we already hit the ground running with all the installed base that we have. We're going to install a lot more with a lot more intelligent equipment and develop some new algorithms. So everything that we have already that we're going to make work and improve and then demonstrate that. So it's sort of a research and development and then a demonstration phase with the Department of Energy. And these are the basic goals, basically create new technologies. That's what the government wants to see. Enhance the grid reliability and also enhance asset utilization. So again, assets in this case being cables, okay, the feeder cables. But because of how we're going to monitor, so this is an example, we can even increase the asset because we want to go into the point of common coupling with the DG, distributed generation. Now since it's Denver, that would be PV, photovoltaic. So we kind of have a connection point. Our goal is to have a connection point with intelligent stuff at the point of common coupling where the solar panels are connected into the feeder. And then we'll also be monitoring at the feeder head. We're also going to try and expand the upstream because we're going to have a device on the power transformer, and it happens to be our transformer 615, but just because of the capability. So we'll be able to monitor the 3-phase voltages on the transmission side, the 3-phase voltage on the distribution side, the 3-phase currents on both the high and low side. And that would allow us to actually create another step of resolution for upstream. Okay, so last year, I just talked about a what if. What if we, and this is also interesting, of course, this is how we all draw the feeders, right? We love drawing these single lines. These are really nice, easy feeders. And then you actually go and you say, okay, that's the feeder. So this is basically the feeder map placed over the feeder model. The feeder model for one feeder placed over the GIS map in that utility that we're monitoring. So you can imagine, even if you have a fault location device that says 1.3 miles, okay, where am I going? It's like make a left, make a right, make a left. So, and these flags just simply meant where we had faults during the monitoring stage that we had. But here's a substation over here, right over here. So the idea, again, is that we can give a story, okay, and then now what we're working on is to be able to say, in the fault segment 25. Right now, what they have to do when they get that fault, they simply start at the furthest ends and do a bifurcation method. Boom, boom, isolate, throw it back in, see if it faults. Come back, see if it faults, and then, and many times they're starting so wide, it takes a long time, and that's running the SAIDI clock, because the customer, of course, is called. These are permanent ones, and so the SAIDI clock. So we can actually give them that fault segment that can help them reduce the bifurcation steps and find that place. And really what I learned, I always thought they were replacing them, but they're actually isolating just to get service back, and then they'll come back later and replace the cable or whatever they find. And that's why I know it was mostly cable failures, not so much. But there were definitely some termination issues in like the switch cabinet. And so what we've been doing now is an offline. We're at the offline method, and we have a pilot feeder we're working with. It has 817 line segments, and then only the ones that have a fault current are considered. And we have 19 cases. I'm just going to show you a few. But the key is that we're using the typical substation data. That's the key. Now, we're going to see if we can get greater resolution with external stuff later on in the project. But right now, we're going to start in the sub. And here are just two cases. What you had was our algorithm is actually showing and delivering these red lines. Based on the fault data that it said, our algorithms in the Station Computer Com 600 said, I think it's at this segment, that segment, this is all the red. And that segment, and that's actually where it was. Green is where it was. We're within one segment, 155 feet. Now, what do you think? You can say, yeah, but so what? I mean, you got to get all these. What do you think if you look at that map? What do you think is another differentiator? If you have this kind of information, you have several areas, what can you compare against to kind of then filter and say, you know what? I think it's here. What do you think data they can use? Where are they calling from? Their existing OMS system that's simply paying attention to where is the greatest concentration of calls. And this is simply another case. And here where there were 5 out of 118 potential candidates. And then in this case, the 1 of the 5 was right on the faulted segment. Were they all that way? No. I'll humbly admit. But that's why it's the beginning phase. We are researching, we are developing new algorithms, and we already have a good start. And that's what we'll be deploying in our DOE project this year. So, takeaways. Well, number one, basically you can do real-time feeder event monitoring from within a substation using existing typical connections. And if you can do it in a relay that also protects and controls that feeder, that's actually the most cost-effective solution. Real-time notifications are valuable so that you can give the early knowledge to dispatcher. Knowledge is power. They'll know, and then when the customer calls, they'll be able to confirm that, okay, I'm really confident. A lot of times they usually have to wait for a certain number of customers. But here, you only need the first customer. If you already have the waveform, and you're seeing a half-cycle waveform, 5,000 amps, all you need is one customer to say, my lights are out, and you have the confidence, send dispatch. And we know where to go because we're giving them the substation and the feeder. In this case, we hope to give them the fault segment. And then I already mentioned the second one, integrating it in the feeder protection device. Thank you for your time.